Good afternoon, everyone. Welcome to week 9 live session on Structural Dynamics course. I'm Danish Bashir from IIT Madras. In the last week, that's week 8, we studied about numerical methods of solution for solving governing differential equations of motion for a single degree of freedom system. Okay, so in today's lecture, we will be studying multi-degree of freedom systems. So up to now, we solved all single degree of freedom systems, depending upon whether the systems were having free vibrations or forced vibrations, or whether the damping was present there or damping was absent there. So from today's week, we will be starting multi-degree of freedom systems. We will be studying the systems where there will be more than one degree of freedom system. So we'll be studying how to derive governing differential equation of motion for multi-degree of freedom systems. Okay, for example, so I am going to start with multi-degree of freedom system. Multi-degree of freedom systems. So multi-degree of freedom systems are those systems in which there are more than one degree of freedom present. So what do I mean by that? For example, we studied this conventional single degree of freedom system like this. We had a block of mass m, mathematical model like this. We had a block of mass m. It was having some stiffness parameter k and damping parameter c. So it was having stiffness parameter k and damping parameter c, and its motion. So all the inertial effects. It was having only one single inertial effect. That's the concentrated mass m, and we were requiring only one displacement or rotation. Here it is only one displacement x of t in x direction. So we were requiring only one displacement, independent displacement, to completely represent the inertial effects of this system. That's why we call it as single degree of freedom system. So for example, if we have more than one inertial, if we require more than one independent displacements or rotations in order to describe all the significant inertial effects of a system, that system is known as multi-degree of freedom system. In multi-degree of freedom system, we can have 2 degree of freedom system, third degree of 3 degree of freedom system, 4 degree of freedom system. So, for example, if I draw a multi-degree of freedom system like this, we have two slab floors. Okay, like this. One is this slab, another is this. Okay, this one. And we are having columns like this. We are having columns like this, which are supported by columns, this column, and we are having one more column system from this side. Okay, so we are having this thing. Okay, we have to make these things floors of equal height. Okay, now they are of equal height, and both columns are fixed at the bottom. Fixed is like this. Sorry. We have one more fixed end from this side. Okay, so we are seeing that. So, for example, if the mass of this floor system is M1, first floor, and M2 is here. So, what we are assuming in this frame that the mass of the whole floor is lumped at the floor level. So that is the mass of all the walls, that is the retaining walls or the whatever the things are present inside the floor, and the boundary walls as well. All the mass is lumped at the floor level. Same for the second floor level, we have M2. And now these masses are lumped at two different levels, so we need two independent displacement in order to completely represent the motion of this system. So we will require one displacement from this side, like x1 of t. Okay, we will require another displacement from this side, x2 of t, in order to completely represent its motion. So we have this. We will assume moment of inertia of this. So this floor will be supported on beam system. So we will assume moment of inertia to be these beams to be very high stiff of a high stiffness. That's moment of inertia is pretty much high. And let the full floor level of each floor will be h. Okay. HH, and it is being dynamically excited by some forces, maybe wind or earthquake excitation is there. So it is at second floor level, it's P2 of T time varying force, and at first floor level, it's P1 of T, okay? P1 of T. So we are required to solve this system and find the governing differential equation of motion of this system under time varying loads P1 and P2 of T. So how we will approach this multi-degree of freedom system problem? So this is multi-degree of freedom system. Okay, how we will approach it? We will be studying it today. So for example, I will draw the free body diagram of each floor. So for floor one, all right, floor one, okay, that is mass M1. If I will draw the free body diagram for the said mass M1, so for example, this is a floor level like this. So it is having mass M1, okay. So if we will see that one more thing I forgot to mention here, that stiffness of this floor is K1, that is the bending stiffness of columns K1, and here it is K2 for the second floor K2. Okay, so it is moment of inertia of beams. Okay, we have this IC is moment of inertia of columns. Okay, this thing. So M1. So for M1, if we will see that because of this is M1 mass. So because of this bending stiffness of the lower columns, when the excitation P1 of T will act in this x1 direction, like in this direction x1 of T will act. So motion is in this direction. This stiffness will try to force the system back to the equilibrium. So for this M1, the restoring force K1 X1 will be in this direction. Okay, K1 X1 will be in this direction. And one more thing is that dynamic excitation at floor level P1 is acting in this direction. P1, okay, P1 of T. And above to the above floor level, so this is having x1 displacement here, and above is having x2 displacement here. So with respect to the floor level 2, or with respect to the columns at the above columns above this floor, it's having a relative displacement of x2 minus x1. So it will be having restoring force in this direction like this. Uh, like this. It will be having k2 x2 minus x1. And using D'Alembert's principle, we have to give one fictitious load. If you guys remember from the first class, we have to give this fictitious load in order to bring our dynamical system into a dynamic equilibrium, so that we can write the governing equation of motion for each time step. Okay, so that force is proportional to the inertia and acceleration of that system, that is m1 x1 double dot. Okay, so writing the equation, summation f along x is equal to 0, we can have m1 x1 double dot along this direction, we have plus k1 x1 along this direction, okay, minus we have k2 x2 minus x1, so it's acting upon opposite direction, so minus, and another p1 of t, so it's acting in opposite direction to the other forces, that's why I'm taking minus, is equal to 0. When we will collect the like terms of x1 and x2, we will get an equation like m1 x1 double dot plus k1 plus k2 uh, x1 minus k2 x2 is equal to p1 of t. Okay, so this will be our equation of motion for first floor, m1 x1 double dot. Okay, so writing the equilibrium equation, using free body diagram for this is fbd of m1, fbd of m1. Okay, so for floor 2 we will be going to floor 2 mass m2. Okay, we have to write the equation of motion in a similar fashion, so I will just copy paste the things from here. Flow 2 is same thing, we have to change little things like, okay, we have flow 2 like this, so we have to modify few things. This is okay, this is k1 of x, this is this, this is this, this is this, this is this, and this is this. Okay, this thing. So this will be m2, this will be, I think, this thing. Oh, and this will be p2 of t, this will be m2 x2 double dot. X2 double dot is the acceleration of the second floor, and restoring force will be acting in this direction k2, and relative motion is x2 minus x1 with respect to the columns, and p2 of t. So writing the equation of motion for this thing, we will have summation fx is equal to 0, and from that we will get m2 x2 double dot, and it's acting this direction. We have k2 x2 minus x1, x2 minus x1 is equal to this direction minus p2 of t, and since it's in the opposite direction we will have the negative sign, is equal to 0. So rearranging the things, and we will get this equation m2 x2 double dot minus k2 of x1 plus k2 of x2 is equal to p2 of t. Okay, this thing we got another equation of motion, so we can write here like this. This we got first equation, This we got as second equation. Okay, one and two equation. So one and two equation we can write compactly in the form of a matrix system of equations. Equation one and two can be written compactly as so actually these are couplet equation. You people will be seeing that x1 and x2 are present in equation 1 and equation 2 respectively. So displacements x1 and x2 are couplet between equations 1 and 2. So we will have when we write these in a matrix form, we will have like this. We will have m1 0, we have 0 m1, and we will have then acceleration of the two masses. This actually m2. Acceleration of the two masses will be x1 double dot plus x2 double dot. This is this thing, and plus then we have stiffness. We will have first term will be k1 plus k2 minus k2 minus k2, and this will be k2. I will tell you people how this things came from. Then we will have x1 and x2, x1 and x2, and then we have p1 and p2. P1 of t force acting, and we have p2 of t another force acting. Okay, so this is a system of equation that we will get for 2 degree of freedom system. Okay, so this thing we got. So actually if we see we will solve this again, we will get m1 x1 double dot. For example, if we multiply this matrix with this vector, this matrix with vector, we will again get separately equation 1 and 2. So these are equation of motion. We have equation of motion for multi-degree of freedom system with d degree of freedom DOF is equal to 2. So we can compactly write it as, so this can be write as mass matrix M. This has displacement vector X. This has stiffness matrix K. This has displacement acceleration vector. This is displacement vector, and this is force vector P. Okay, we can write M times X double dot plus K times X is equal to P of T. Okay, this is the basic thing you have to remember. So depending upon the degrees of freedom, we will be having these order of this mass matrix or stiffness matrix. So if we have n degree of freedom system, we will be having n by n mass matrix and n by n stiffness matrix. There are other properties of these mass matrix and stiffness matrix which we'll be discussing in a couple of minutes. Okay, so we have these things. We have where we can write it as, where we have to write M as mass matrix, mass matrix, K as stiffness matrix, stiffness matrix and other things as x double dot. We know that is acceleration vector, x is load vector, displacement vector, and p is load vector. So we have the things like this. If we will look at the typical this uh, so now we will be solving one problem for this. So for this, so we were able to get the mass matrix and stiffness matrix after writing the equilibrium equation of motion and all the things, doing these long cumbersome computations, and only after that we arrived at mass matrix and stiffness matrix. There are other shortcuts by which we can write mass matrix and stiffness matrix as well. So we have mass matrix like this. We have first stiffness matrix K, which is given by like which has elements one any particular I comma jth element, ith row and jth column given by Kij. Okay, where we have some notation for this. Kij is, it is actually Kij is the force produced at ith degree of freedom due to displacement at jth degree of freedom. So actually what it is, if we I have n degrees of freedom of motion. So for example, I am looking giving the force at, I'm giving the displacement at jth degree of freedom and looking at the force at ith degree of freedom. Then that is known as Kij. That is the stiffness of that degree of freedom. For example, if I am looking at K11 element of the stiffness matrix, that means that means that the force that is produced at 1 degree of freedom due to a unit displacement applied at that degree of freedom. Okay, so Kij is actually it is it is nothing but force produced at force produced at ith degree of freedom, ith degree of freedom due to unit displacement due to unit displacement at jth degree of freedom. Okay, this is nothing but this is the notation meaning of this notation. So for example, if we will see for the previous frame that we already draw, I will redraw it here again. So we were having, I will make that frame roughly like this. We are having frame like this. Okay, it was having fixity at both sides, both points. Okay, this was it is x1 degree of freedom system. This was x2. Okay, so it was having 2 degree of freedom. Okay, so for example, we are giving we want to find k11. Okay, so k11 I told you we have to give at 1th degree of freedom system we have to give one unit displacement and note down how much force is produced there. So this is degree of freedom 1. Okay, this is degree of freedom 2. You keep that in mind. So taking this thing, so this column system is like this again. Okay, so this is uh, degree of freedom 1. Okay, so we are giving a unit displacement x1 is equal to 1 here. Okay, x1 is equal to 1 unit displacement. So we will see that these columns will be like this, will be going to this. So it will be here like this thing. Here it has stiffness K1, it is K2. Okay, and we have x1 and 0, x2 is equal to 0. We have to give 0 because we are finding K11. Okay, we will be getting this like this. Okay, things like these. Okay, K11, K22. So it will give us here K11. What is the force produced at this degree of freedom? It will give us K11. And another thing is we have to find K12. Okay, here. So K11 is we are giving force at this degree of freedom. So force produced at F is equal to K1 plus K2. Restoring force is actually equal to, so restoring force at this degree of freedom will be produced as upper, from upper floor it will be K2 into X is 1 and X2 is 0, and it will be K1 into 1, K2 plus K1. Okay, so it's like this for K11. So our K11 term we got as K1 plus K2. Okay, okay. So for another thing, now we are giving unit displacement. It was unit displacement, unit displacement at degree of freedom 1. Okay, so we will give now unit displacement at degree of freedom 2. Okay, so for that thing the column system will be like the same one. So here this column will not move, lower column will not move up to this point. From this point to above point it will not move because there is no displacement. So we are giving one unit displacement here like this, so this column will be shifted to like this. Okay, so we are having this, this we will get here as jth degree of freedom. We are applying unit displacement, so it will be 2, and we are seeing what force is produced here. It is K12, and we are applying force here, this one, this at second degree of K, and it is K22. Okay, so what we will be seeing that is we have this thing. It will be equal to K, force will be equal to K. So sorry, this will be K21. It will be K21, and both will be equal to minus K. Okay, K21 is equal to K12 minus K. Similarly, if we proceed in the similar manner and for finding K22, we will give unit displacement at 2 and find the force produced at 2. It will be positive K. So similarly, you can find K22 is equal to K. So our stiffness matrix finally will be looking like this. K will be equal to, it's actually first K11, it is K12, it's K21, it's K22, okay? So we will substitute all the values here. K will be equal to, it is K1, K11 is K1 plus K2, it's minus K2, minus K2, it's K2, okay? So by this method we are also able to find the stiffness matrix, okay? So by Kij method we have to remember that is the flow force produced at ith degree of freedom due to display unit displacement jth degree of freedom and zero displacement all other degrees of freedom. So while finding K11, we have to give unit displacement at one degree of freedom and see the force there, and zero displacement and all others. And for finding K12, K12 is the force produced at one degree of freedom and giving unit displacement second degree of freedom and zero displacement at all other degrees of freedom. So that will be equal to K12 and K22 giving unit displacement at 2 and finding the force produced at 2 itself. We got this matrix. Here we can have K11 as, since I will write here one thing I forgot to write here. K1 will be equal to, we know it from structural analysis. K1, okay, K1 we are having in this bay we are having two columns, okay, we are having two columns, so it will be 2 into 12 EI by H cube, okay, stiffness, bending stiffness of this column 12 EI by H cube, okay, so it will be EI1, actually it is floor level 1, it is 24 EI1 by H cube, EI1 by H cube. Similarly K2 for columns 2 it will be again 24 EI2 by H cube, okay. Okay, this is the thing. So it is having I1 moment of inertia, it's having I2 moment of inertia. So I wrote all these things. How to get the mass matrix? In mass matrix we have to do in the same manner where we have to give Mij is the inertial force produced at ith degree of freedom due to a unit acceleration at jth degree of freedom at zero acceleration at all other degrees of freedom. So for that thing I will write here again for mass matrix, okay. Here I have for deriving stiffness matrix. This is the procedure for deriving stiffness matrix. And what is the procedure for deriving mass matrix? I will show you that. I'll just briefly tell about that thing. Okay, for we have to see another thing now. For deriving mass matrix, okay, mass matrix M. So what is the procedure for the same? We will just briefly highlight that and then we will move forward. So it's actually each element of mass matrix M may be represented by Mij, which represents inertial force produced at ith degree of freedom due to unit acceleration, at jth degree of freedom and 0 acceleration at all other degrees of freedom. All other degrees of freedom, okay? All other degrees of freedom, okay? So we are having things like this. Mij is the inertial force produced at ith degree of freedom due to unit acceleration at jth degree of freedom and zero acceleration at all other degrees of freedom. Same is in the case of Kij is the force produced at ith degree of freedom due to unit displacement at jth degree of freedom and zero force, sorry, zero displacement at all other degrees of freedom. Zero displacement at all other degrees of freedom system. Degrees, okay, freedoms. So in case of our for deriving our mass matrix, for example, we have to get the mass element m11. We will give unit acceleration at 1 degree of freedom and note the inertial effect, inertial force produced at that point. We will note that at degree of freedom 1, we have mass m1 lumped there. So it will be having acceleration 1. So inertial force produced will be m1 into 1. So the correspondingly, the inertial force will be produced as m1. Similarly, as at second degree of freedom system, we are giving acceleration equal to 0. So m21, that is m21 will be 0 and m12 will be also 0. For m22, we have give unit acceleration at 2 degree of freedom system and c inertial force produced at second degree of freedom system. So it will be m2 times 1, it will be m2. So our mass matrix will be diagonal, okay? I will quickly write that. So we have this thing. We have a frame like this. We have a frame like this. We are trying to get its mass matrix. We are having this floor level. We are having this one level one. This is having we are having level two. So for K11 we are having lumped mass M1 here. We are having lumped mass M2 here. So I already told you to get M1, M11, give unit acceleration at 1 degree of freedom system. That's x double dot of 1 is equal to 1 and 0 acceleration at all other degrees of freedom. Okay. If we see the inertial force produced at this point is will be like this. Okay. Sorry, this will not be covered. Okay, this will be like this. So it will be here x2 double dot is equal to 0 and mass at their point is equal to inertial force produced is m2 times 0 is equal to 0. Inertial force produced at this point will be m1 times 1 will be equal to m1. So actually m11 is the force produced at 1 due to acceleration of unit acceleration at 1 the degree of freedom system will be m1. Okay. Similarly giving x2 is equal to x2 double dot is equal to 1 here like this and x1 is equal to 0, x1 double dot is equal to 0, it will be m2 times 1, it will be m2 times 1 is equal to m2. Okay, so m22 will be equal to m2. So our mass matrix m written in the form m11, m12, m21, m22 will be equal to m1 0 0 m2. Okay, here again m12 is equal to m21 is equal to 0. You can check that also. Okay, this will be the mass matrix. So one thing important to note here that as our mass was lumped at the points where the degrees of freedom are exactly defined. So here is the degree of freedom here DOF, and here is the degree of freedom defined at DOF. So exactly at the same point mass is lumped. Exactly at second degree of freedom system, mass is lumped. So uh, for systems where the degrees of freedom are defined and exactly at the same point masses are lumped, we get a diagonal mass matrix. That's all the of diagonal elements are zero. There is a huge benefit of getting this diagonal mass matrix. We will see in coming lectures that this diagonal mass matrix reduces the computational cost to a very huge amount. So if we have a non-diagonal mass matrix, then we will try to diagonalize it and then use the same mass matrix. I mean to say that improved mass matrix in the for the computational calculations because it reduces the computational cost. So having so we have to decide the degrees of freedom of our multi-degree freedom system in such a way that mass should be lumped at that point. So important point to note here is uh, if uh, degree of freedom is uh, defined at points where mass is lumped, we get diagonal mass matrix. Uh, benefit beneficial. It's very beneficial to get diagonal mass matrix. Okay. So we got these two things. Then we can go further. Now we'll see one more thing is that now, for example, same system that is this initial system, this one. Here, if we assume P1 of t and P2 of t are equal to 0, that is free vibration case, it is that there. Then we will try to solve this system of equation, that is equation system A, okay? We will try to solve equation system A, okay? Equation system A. So we will go to free vibration problem for multi-degree of freedom system. Free vibration problem. So for free vibration problem, if we see for free vibration problem from equation first, not from first, from equation A. Equation A. Equation A was like this. We were having M1 here, 0, 0, M2 here. Same frame system. We have accelerations at degree of x1 double dot, x2 double dot, and then we have stiffness matrix as already derived k1 plus k2 minus k2 minus k2, and it's positive k2, and it is here we will assume P1 is equal to P2 is equal to 0 because it's free vibration problem, okay? X1, X2 displacements, and here the load vector is 0, okay? It's free vibration problem. The system is initially being excited with a very small point load, and then the system is allowed to vibrate on its own. That's known as free vibrations. And assuming here damping is not present, C is equal to 0, that's damping undamped, okay? Free vibration problem. So for degree, so we will assume for single degree of freedom systems, okay? And here is undamped, okay? undamped case we are taking here. We will assume that the solution of this above equation system x of t is given as c sine pt plus alpha. Okay, we will just make an assumption like this: pt plus alpha. Okay, we will check this can be a solution. Checking if it is a solution. Okay, checking if it is a solution. For that, we will have to write for independent displacements x1 of t, x2 of t. We will have to write it as amplitudes x1, x2. We will have sine pt plus alpha. Okay, pt plus alpha. Okay, so acceleration correspondingly will be equal to x1 double dot x2 double dot of t. If you will differentiate this equation twice, it will be acceleration will be x1 x2 amplitudes, initial amplitudes, minus p square sine pt plus alpha. Okay, where p is a natural frequency and given by stiffness or root square root of stiffness of system divided by mass of the system. So if we will substitute, this is equation 3. So we assumed 4 and we got this 5. So equation 5 to be substituted in equation 3, we get, when we substitute it there and get the necessary this collections, we have m1 p square 0 0 m2 p square. Okay, and we have x1 double dot not, we have x1 x2 plus, we have k1 plus k2 k minus k2 k2 minus k2 minus k2 k2 x1 x2 x1 x2 uh, we have times this whole will be sine pt plus alpha sine something something is equal to 0. So the sine pt plus alpha will not be 0, otherwise it will not be a time varying solution for this. So for that thing, this has to be 0, because again x1 and x2 cannot be 0. So x1, if x1 is equal to x2, it will be trivial solution. Okay, is equal to 0, that will be trivial solution. Trivial solution. For non-trivial solution, we should have, this will have a solution, this will have solution, solution 1, determinant of the matrix on the right hand side, that is, we have the matrix like this. I forgot to write it. It is k1 plus k2 minus mp square, k1 plus k2 minus m1 p square minus k2 minus k2 k2 minus m2 p square m2 p square times x1 x2 should be equal to 0. So for non-trivial solution, determinant of this matrix should be 0. That is, we have determinant of this thing, we have k1 plus k2 minus mp square, p square plus minus k2 minus k2 k2 minus m2 p square. It should be equal to 0. So for solving this equation, we will get the equation in terms of quadratic form like this. So we will have, if we will solve this, we will get k1 plus k2 minus mp square, m1 p square times k2 minus m2 p square, minus minus plus and minus k2 square, okay, is equal to 0. So it will be a quadratic equation in p square. So finally when we will, it's m1 m2 p power 4, okay, plus we have m1 k2 plus k1 plus k2 m2 p square, okay, this will be p square plus k1 k2 0. So this is the equation. It is quadratic. Quadratic in p square, okay. So we will try to solve it. So if we assume that the k1 is equal to k2, let's assume that our system is k1 is equal to k2, stiffness of both the floors is equal to 0, column is equal to k, some k constant k, and mass of floor 1 m1 is m, and mass of above above it is half of the below floor m2 is equal to 0.5 m. Let's take these assumptions and try to solve that our problem, okay. Assume, and we will get this equation as 6, okay. Then we can have when we put these things in this, we will substitute back this thing in this. We will have p power 4 minus k by m. After dividing by m square throughout, we have 3k by m p square, something like this, and inside it will be something like this, plus k square by 0.5 m square. It will be equal to 0. If we will take p square by m by k is equal to lambda, we will make substitution. Let p square m by k is equal to lambda. So by making this substitution, we get a simple equation as lambda square minus 3 lambda plus 2 is equal to 0. When we will solve it, we will get lambda 1 comma lambda 2 is equal to 1 comma 2, 1 comma 2. So it's actually p square m by k 1 comma 2, okay. So we are having two eigenvalues of this equation, that is lambda 1 is equal to 1 and lambda 2 is equal to 2. So these two eigenvalues give the first two natural frequencies of this to second degree of freedom system. So that is p1 is equal to lambda 1 p square k by m, and p2 square is second natural frequency or frequency of the second mode is equal to lambda 2 k by m. Okay, this is the simple thing. So associated with this each mode, there will be a specific mode shape. That is the vibrating pattern of our given structure under the influence of given natural frequency. So what we have to do, we have to substitute this back lambda 1 is equal to 1 and correspondingly find x1 and x2, and lambda 2 equal to, and correspondingly find x1 and x2, and we get the mode shapes like this. For mode shapes, we substitute lambda 1 and lambda 2 and get the corresponding mode shapes. Corresponding mode shapes. Thank you. This was all for today. Thank you everyone for joining this session.